Hello, it's Keith here, and this is lesson 67 of my platform-specific tutorials, and we're looking at the 10K special again, which is the video you can see here, covered up by my rather nice advert for my book. Anyway, we're going to be going into the details of the CPC Plus code today. The video is quite big, it's about 480k, that's 450 frames, so it is going to be quite big, but we're streaming it from a cartridge. Now, the way the cartridge works on the Amstrad CPC is it's a ROM file, and it maps to the C000 onwards range in 16k blocks. So we're paging in these 16k blocks into memory and reading into them and then writing back to the screen. And we can actually read in from the cartridge and then write to the same C000 range, and that will write through to the screen. So reads come from the ROM, but writes go to the VRAM. So that's quite handy for us. But we're going to deal with those paging. We're also going to deal with the palette switches. We're using the CPC Plus palette. We're finally going to discuss the Chibi Tracks software, which is my new music player, also known as Chibi Sound Pro, Chibi Tracker Pro, that kind of thing. It's got different names for the different parts of it, but this is my music software which I'm working on. Anyway, that's what we're going to be discussing today, so let's get that out of the way and let's go over to our source and let's take a look. So the first thing I want to discuss is the cartridge file. So we're building a CPR cartridge. The program we're using to do this is called Build CPR. Now this is a very simple program which takes a binary file and converts it to the CPR format. So we're going to build that binary file ourselves, and we're literally doing it with a copy command. So basically, we just need to have 16k binary blocks that represent the different banks of the cartridge. Now, the way we're doing things is we're actually using some template ones that are going to simulate the MS-DOS basic and the firmware. So you can see we've got these three here for the basic operating system and also the disk operating system. These have been lifted from the NoCart program. I can't take an ounce of credit for these because I don't deserve an ounce of credit for these or possibly anything else. But these are taken from NoCart, which is a disk emulation system. It's designed so that if you've got a disk program, you can convert it to a cartridge very quickly. It's quite convenient in that it provides an operating system for us, but I don't actually want that disk part. So what I've done is I've modified it, but we're using it as a sort of template. Now, the modification I've made is to the DOS part of this. Now, if you go to the NoCart website, you can download the patches for the ROM and you can download the source code for the program. And so what I've done is I've downloaded the patches and I've modified the patch that is the final part of the initialization routine. Now, rather than reading in from the disk, what my version does is it copies this ROM copy routine into the RAM at memory address A100. So this is relocatable code. So, and what this is going to do is it's going to basically copy 2.5 banks, 2.5 16k banks from the cartridge into RAM at memory address 100 in hexadecimal onwards. So this is going to be the start of our program, and then it's going to execute that program. The idea being that we have the 100 to A000 range that is now in RAM that has been copied from our cartridge, and this can do any other tasks that are required later. Now, this is enough memory for the frame pointers for our video file and our program itself. The rest of the data, the command stream and the bitmap stream, these are banked in as required. So that's the modification I've made to the DOS file, and that is how I'm building my cartridge. So basically I have modified the MS-DOS. So that's how I've modified things so that my program can start up the way I want it. And that allows me to start my program at memory address 100 and have loads and loads of memory available to me for my program and things. So that's what we've done there. Now, at the start of our program, we are initializing the CPC Plus functionality, and we're writing in our own interrupt handler, and we're running this thing called Chibi Sound Pro init. And then we're starting a song. Now, Chibi Sound Pro is a music driver. This is a platform-specific driver for better sound than my original Chibi Sound driver. This then links into a multi-platform music player called Chibi Tracks, and then I have something called Chibi Tracker Pro, which is the music creation software. So there's three parts to this. Chibi Tracker Pro is Windows based. Chibi Tracks is multi-platform on a per processor basis. And Chibi Sound Pro is the platform specific sound driver. So there's one driver for the CPC, one driver for the Sam Coupe, and so on. Now, during the interrupt handler, on the CPC, the interrupt happens 6 times per frame, but we only want the music to play once per frame. However, because we're disabling interrupts and things, it gets a bit sporadic. So rather than checking if we're in VBlank, what I'm doing is I'm only updating the sound every 6 frames here. We've also got a frames tick count here, which is counting how many frames have occurred since the last frame was drawn, and this is so that we can hold the frames on screen. And if a frame took like a full second to draw, for example, we don't want to wait anything. But if a frame took only 1/100th of a second to draw, we might want to wait a few frames. And so that's what that frames tick is allowing us to do. Now, Chibi Tracks itself does not use shadow registers. It only uses AF, BC, DE, HL and IX. It doesn't use IY either, so we don't need to do very much for it to work, and it provides adequate sound music. The music file it's playing today is a converted version of the original Chibi Akima's theme, which was created in Arcus Tracker. Chibi Tracks is not as advanced as Arcus Tracker. It's much more limited because of its multi-platform nature. It can't use envelopes and things, but it can provide minimalist basic music that is okay, and it works on 6502, 68000 and a Z80, and it will probably be ported to other systems. So it's designed to be multi-platform. That's the intent. So we're going to cover that later. I'm not covering it in detail yet, but there's going to be a whole tutorial series on Chibi Sound and Chibi Tracks later on. But that's the basics. Now, the CPC Plus, I've covered this before, but in case you don't know, CPC Plus functionality was locked out and they claimed it couldn't be used except on cartridges, which was a lie. You have to write a secret sequence, and so there's this initialization routine which will turn on the CPC Plus functionality. We then out this 16-bit value to turn on the CPC Plus registers, and we out this value to turn them off again. And if we want to set a palette, we basically write that palette to memory address 6400. There are 2 bytes per palette entry, and so this function here will set a palette, and we've got a variety of palettes here. And the palette format is 1 nibble per channel with the top nibble unused. So these are the various colors. So we've got 3 palettes that we're using as part of our sequence. And the pointers to these are encoded in the frame list here. As you can see, we've got plus palette blue here. And this is defined when the speed is 255, which is never used for any other purpose. Now, how do we use these? Well, at the start of our sequence here, this is the start of our loop, and we're loading in the pointer to the sequence, which is the list of frames. So this is actually building the frames into a video. If we didn't have this, we'd just have still frames, I guess, in theory. So what we're doing here first is we're clearing the frame tick count here, and we're then loading in what is effectively the delay, the 3rd byte in, and if that's 255, then this isn't actually a graphics frame, this is actually a palette. So we're loading in the palette address here, and we're running that set palette routine and then skipping over that data, and we're continuing. Now, when we've got a frame address, we're loading that into D&D here, and we're seeing if that is FFFF. That's impossible because a frame will never start at the end of a bank, so that is an impossible address. Again, we're having to deal with bank switching here. So now what we're going to do next, if we've got a valid frame, is we're going to load in the bank number from offset IX plus 2. This is the bank number, and we're going to now page this in. Now basically we've got this value CartStream default here. We need to write a 16-bit value to page in a bank number. Now to page in the first free bank, we use DF84. Now the 84 part is because we're paging in the 4th bank. Now this is the start of the command stream. The pixel stream will be later on, and the exact address will vary depending on the size of the command stream. So I've got this massive calculation here to calculate the correct command to page in the first block of pixel data. Now when we out this value, this will page in one of the blocks of the cartridge to the C000 to FFFF range. And what we basically need to do is we need to take this BC value here and then add the offset for the bank number that we actually need to page in, so that we have the correct bitmap data, so that we have the correct command data for this section. We're then storing that in CartRam stream here. This is a temporary variable that's used, and this is because the command stream may span over 2 banks if it's large. As I say, it will never be at the last byte of a bank, but it might have a few bytes before the bank ends. So that's why we're storing that here. We're then paging in the bank, And what we're doing here is we're basically stripping off the top 2 bits of the 16-bit address and forcing them to be in the C000 onwards range. And this is because, as I say, the command stream on the CPC Plus is always in the C000 onwards range. So we want to ignore and force those top 2 bits there. Now, if we were only working on the CPC 6128, for example, we wouldn't want to do that. And in fact, if we were doing bank switching on the 6128, we would actually want to use the 4000 to 8000 range, because that is the range that can be bank switched in memory on the Amstrad CPC. So that's what we're doing there. We're correcting our memory address here before we start processing that stream. Now, as I said before, there is a command that allows us to do a bank switch. 70 is a bank switch request, and the bank switch basically will take the previous bank and increase it by 1. We're always going up in ascending order there. So once we've done that, we're then setting the next source byte of the command stream to C000 here, because we're starting from the very beginning of the next bank. So that's how we're dealing with the bank switch within the command stream. Within the pixel blocks, a pixel block will never span 2 banks. And basically what we're doing for the pixel blocks, if the pixel block is only using a 1 byte address, then it's always in the first bank. The basic pixel blocks are always just the first handful. If it's a very large video file, then we would end up using 2 bytes very quickly. And in that case, it's the top 5 bits of the address. Remember, there are 2 bytes of the address after the pixel block command, but there's an extra 3 bits that are included in the command itself. So there's the 3 bits of the command, the bottom 3 bits of the command, and the top 2 bits of the 16-bit address become the actual bank number. And so we're adding those to the start bank of the pixel block, and then we're outing that to select that in the C000 range. And again, we're forcing the C000 range here to select that we're going to be reading in from that C000 onwards range for our pixel data. So that's how we're dealing with the bank switching there. And that's basically all of the tricks that we've had to do here. Now, as I say, there's nothing really that means that we couldn't do this on the Amstrad CPC. This video program was written for the Amstrad CPC originally. The problem is, you don't have access to the huge memory resources of the CPC Plus. You could use a 6128 with a 512K memory add-on, and then you could do this on the regular CPC, but you'd have to read in all that data from disk. So the cartridge is far more efficient for a simple demo, but as I say, there's nothing here that's being done that's CPC Plus exclusive apart from the colors, and you could use the regular color palette if you preferred. Anyway, there we go. That's the end of this. If you like what you've seen, please like and subscribe. If you want to support my content, as I said earlier, you can buy my book or you can back me on Patreon, and that's how I can justify writing these kind of complex tutorials. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.